Hello everyone and welcome to another Seds Online webinar. We're really pleased to be able to offer all of these events to you for free thanks to generous sponsorship from the International Association of Sedimentologists, the IAS. This week we're welcoming Cédric John, who is from Imperial College London. Now Cédric completed his PhD in 2003 at the University of Potsdam in Germany, and then went on to undertake a postdoc position at the University of California. In 2005, he began a position as a staff scientist for IODP at Texas A&M University, and then moved to Imperial College London in 2008, where he set up the research group Carbonate Research. Cédric is also a fellow of the Data Science Institute at Imperial College London. In 2013, Cédric was promoted to senior lecturer, and since 2018 has held the role of reader in carbonate systems and carbonate reservoirs. So today Cédric's going to be talking to us about his research on technologies to improve quantitative interpretations of carbonate rock images. So without further ado, I'll hand over to you, Cédric.
All right, well, thanks a lot, Catherine. Thanks a lot, everyone, for being here in my small office at Imperial. It's great to be able to welcome the world essentially home. Good afternoon if you're in the UK, or good morning, good evening, wherever you are. So indeed, I will talk about emerging technologies to improve quantitative interpretation of carbonate rock images, but really in a nutshell, what I mean by this is neural network and deep machine learning, deep learning for carbonates. I want to acknowledge that this is not just my work, it's also the work of my students, and in particular, Sarina Kanagandran, Sarina Kanagandran here, who's done a master with me, Harriet Dawson and Sarah Baroudin. So you'll have an opportunity to see their contribution throughout this talk. And there's no science without money, unfortunately. So please let me thank the CDT Oil and Gas for a studentship given to Harriet, as well as the King's Studentship Malaysia given to Syra. Right, so without further ado, why is digitalization and numerical approach important in sedimentology? Why is there so much noise about this? Well, there's many ways to answer that question. One of them is to look at the energy sector. And what is very clear is that if you look at the demand for energy, it has been increasing over the last 15 years. And in part, it's driven by China and India, by those large economies that are up and coming. So there is more and more demand for energy. Granted, maybe during COVID, we had a little dip, but the general trend is towards the need for more energy. And renewable energy is in the mix, but oil and gas still forms the backbone of the energy we're using. And if you compare this, the left graph with the right graph, which showed essentially the number of new resources that were found over the last 40 years, you can see that the trend is for ever smaller discoveries in terms of oil and gas. So that means that we need to be more efficient at finding new resources, but also be exploiting new resources. And in that case, numerical approaches, numeralization and digitalization plays a big role. So more specifically, I'm going to talk about core digitalization. Why is core digitalization, in my opinion, important? Well, if you look at an IODP core repository here, we have an abundant record of cores that were taken at very high price from the seafloor. Some of those cores become famous, they're the superstar, and everybody talks about these specific cores, but a lot of them go basically ignored and stored in a repository and never looked at ever again. So it's almost like an untapped resource, and it's a very expensive archive. Now, facies or core description is important. I'm going to give you two examples of why it's important. Here I'm going to show, for instance, that petrophysics, so petrophysical classes and rock typing are often underlined by facies. So it's often based on facies. And as an example, you have the Lucia classification here. So doing a good job at describing cores matters because ultimately this is a criteria that we use to distinguish petrophysical classes. Now, even if you look at things that are more, let's say, forward modeling or modeling related, even geostatistical modeling, ultimately, when we use these tools, we want to calibrate them against the portion of the reservoir or the portion of the geology that we know. And this calibration often reverts to environment of deposition, in other words, facies. So it is important to describe cores and to describe facies well. Well, luckily, in carbonate, we actually have a clear classification that has a quantitative basis. It's the Dunham classification as extended by Embry and Cloven, and you see it here on the screen. So I'm not going to go through the classification. I assume you know it. If you don't, it's not that important. What's really important is to realize that it's quantitative because we have cutoffs cutoffs in terms of percentages of grains, for instance, or in terms of size of the grains. Now, those cutoffs are arbitrary to some extent, but nevertheless, it's a convention that everybody uses. So with such a good classification that has a quantitative nature that everybody agrees on the quantification, surely we must do very well. And also, it's been around since the 60s, so we've had time to train people to use it. So how good are we at classifying cores? Well, it turns out Stephen Lockyer did a study where he distributed some artificial thin sections, so pictures of the artificial thin sections to multiple labs, including my own. And everybody could look at the thin section, it was all anonymous, and come up with a classification name for those carbonate thin sections. So I'm showing you here one example. That's a great paper. I recommend that you read it, the Lockyer and Ginebi 2015. So here's an example of a waxstone thin section. Okay, it's clearly a waxstone. And here's how the 60 individuals who took part classified this waxstone. And you can see that only 8 participants said it's a waxstone. And then you have a huge tail of different classification names. Some of them have the term waxstone in them, like a molluscan, a bioplastic waxstone, for instance. But a lot of them don't have waxstone at all in their name and are, just plain wrong. So we're not really good if you look at this. It's kind of a scary realization, because that means if you have a team describing the same thin section or the same interval, they will come up with different classification name. So how can we actually reconcile this problem? But I think what's more worrisome is when Stephen did his study, he also asked people to rate how hard they thought the classification exercise was. And for this one thin section here, pretty much everybody said, nah, that's an easy one. That's a very easy thin section. And yet, there's a spread of classification, and that's a worry. So I'm going to posit here that with modern technology, we can sort of walk away from the human classification, which A, is time consuming, B, leads to some boredom, so it means your attention goes down, and C, as we've seen in a previous slide, can be quite basically variable and not very repeatable, so not very good for quality check and things like this. And what we can do is we can use scanned version of thin section or cores, and we'll focus on cores for this particular talk. So we'll use things like this that are high resolution core scans, mostly from the ocean drilling program. And we'll use automation to do the work for us. And sadly, automation is not yet a robot, humanoid robot that does all the work, take the notes, and brings you a coffee. But by automation, I really mean we'll use coding. Okay, we'll use mainly Python, although we do a little bit of Scala in my group as well for machine learning. And we also use libraries that are public domain, such as TensorFlow that was developed by Google. So before we go more into the technical detail, I'd like to talk about one advantage. You can call it maybe the social advantage of the digital rock in the current era, the COVID era. If you wanted to go and do a core description in a core lab right now, this is probably the kind of PPE that you would be required to wear. Not very comfortable, kind of scary. Now, I'm happy to reveal the official PPE required for digital rock, much more comfortable, much easier to put. That's a side advantage because you can work straight from your home or straight from your desk. Okay, but jokes aside, let's look a bit more in detail. at machine learning and the different types of machine learning. So let's define what machine learning is. If you've not been in the cave for the last 10 years, you've heard the term machine learning. It's everywhere in the news. In pretty much every industry now is really centered on machine learning. And the UK also has an ambition of becoming a leader in machine learning. But what is it exactly? It's actually, like many simple things, not necessarily simple to define. But one definition would be to say that machine learning is the art or science of programming an algorithm by data without explicitly programming it. So in other words, you have an algorithm that you feed data to, and that algorithm learns from the data structure and then becomes better essentially at doing the task you want it to do. In machine learning, we can recognize two big families of learning. One is unsupervised learning, where essentially you give no label to the data. So you basically have a bunch of data, you give it to your computer and you say, hey, look at this data, tell me what the structure of the data is, and try maybe to do some clusters to tell me, what relationship you can see there. And this is a great way to explore data, for instance, or to find new relationship that you had not thought about before. But the bulk of machine learning is really in this domain now, the supervised learning domain. In supervised learning, unlike unsupervised learning, we give training data to the algorithm, and this training data comes with a label. In other words, we tell the computer what the data means. We give it a name, or we give it a value, a number. And then it's the job of the computer or the algorithm to basically find an algorithm to find parameters in an algorithm to be able to do a good job at classifying or regressing the data. So today we'll talk about classification, only about classification, because in supervised learning we have two types of application. One is classification, one is regression. Regression is pretty straightforward. You basically have a bunch of data. It's a continuous data set, and you're trying to find the best algorithm within that data set that allows you to be predictive about a given value. Classification, as its name implies, you're trying to basically separate data clusters into classes so you're able to classify something that you give to your computer. And because today we'll talk about core classification, naturally we're looking at classification algorithm. Now there's many algorithms for classification. Some are simple, some have been around for decades, some are less simple. And we tried them all. Oh, I always forget you have to click. We tried them all, but really when you look at image classification and things like a core classification, you have to look at neural networks. The other classifications we use just do not perform as well. We tried random forest, we tried other algorithms, but they do not perform as well. So we use neural networks. So what are neural networks? This is a simple diagram of a neural network. I took it from this resource here, so you can always go back to look at it. And I'll walk you through a very simple neural network. And you'll see that we don't usually use such a simple architecture, but it's better to start simple to understand what we're doing. So a neural network has neurons or artificial neurons. Those are those little circles here. And these neurons are organized into different layers. We always have an input layer. That's where you input your data. If you input image, then the size, in this case, I put 3 neurons, so that would mean that we have 3 inputs to this neural network. But with an image, the size of your first layer would be equivalent to the pixel dimension of your image, plus, if it's a color image, the 3 layers, so RGB. So you multiply everything by 3. And then, of course, at the end, we always have an output layer. That output layer is the classifier. It's where all the good stuff come out. In our case, because we're doing classification, we'll have more than 1 neuron. In effect, we'll have exactly the same number of neurons as we have a number of class. So in this simple example here, we would have 4 classes as our output. And the magic happens in the middle, in what are known as the hidden layer. Hidden because they are between the input and the output. And you notice that between these neurons and between the layers are the black arrows. These are connections, okay? These connections are equivalent to human synapse, if you want, in the brain. And these connections have a weight associated to them. They're not all equal. At first, we distribute that weight in the different connection completely randomly. Then we take data and we start training our network. So we train our network in what is known as a feed-forward. That's why often you'll find the term feed-forward neural network. So we give an image or we give some data to the network with those, at very first, it's completely random distribution of weight. And that network does its best to come up with a prediction. At first, the prediction is going to be pretty bad, probably around 50%. But you know, we will see in the next slide that we can improve this, of course. Otherwise, there is no point doing it. One thing that is maybe important to know is that once we have fed all of the data that we have for the training to our neural network, we call this one epoch. Okay, so we can train our network. Typically, we will train the network over tens or hundreds of epochs. So multiple times the same data set will be feed forward into the neural network. At the end, we compare the prediction of the network with the actual classification, the labeled image that we have, and there's going to be some error. And we do what is known a feed backward or back propagation of the error back to the network. And for those connections that basically led to wrong answers, there's going to be a penalty, and the ones that led to right answer, we're going to increase their weight. That's why over time, you increase the weight of the connection that makes sense. And the goal here of this game, of the training game, is to come up with a network where the weights are adjusted in such a way that if you feed forward an example, an instance of class 3, the network will automatically predict that the highest likelihood for the classification is class 3. So in essence, in very simple terms, this is how a neural network works. Now, unfortunately, those very simple architectures, they've been around actually for a very long time, since the late 40s, early 50s. They were known as the perceptron, and they had only one hidden layer. And that the problem at the time is because the computing power was not high enough, sufficient enough, and because the architecture was so simple, these architecture actually did not perform very well. But over the last decades, there's been an explosion in computer power and in network. And what you see here is a network called Inception. We did not write that network. It's actually Google who wrote that network, but we will use that network for our research. And you can see immediately that you can recognize some structure, an input layer here, and a final output layer here. Okay, so that you're very familiar with. But look at the number of layers in between this input and this output. You can see that it's very deep. There are many, many layers called inception cells that are basically stacked together. So that is what is known as a deep neural network, and that's where the term deep learning comes from. And those deep neural networks require a lot of data to be trained. However, they also perform very well. And that particular type of architecture is known as a convolutional neural network, or in short, a CNN. So let's look a bit closer at the C in CNN, which is the convolution part. If you look here at this, basically the inception cell, you can see that we start with a pre-activation, and then we have these filters here, these blue things called convolutional filters. So what is a convolutional filter, and what does it do actually, and why are those particular architecture so efficient at doing data analysis on image? Well, a convolutional filter is basically relatively simple to understand. What a convolutional filter does is it takes a window. So here in this example, I have a window of 3 by 3. So it will look at 3 pixel by 3 pixel, and it will essentially shrink the information of these 9 pixel into 1 pixel. Okay, so that filter really is here to reduce it. It reduces the dimension of the image to its essence. So by moving that convolutional filter by 1 pixel each time over this image here, you end up with a much more reduced data set that is essentially 9 pixel or 9 data point big. And you can apply that convolutional filter twice if you want. So you could apply it once more on this to end up with only one number that is characteristic of all of these pixels here. Okay, and the interesting thing is you can do convolutional filters at different size. So here's a 3 by 3, here's a 5 by 5. And you can see that sometimes we also just have a simple 1 by 1 convolutional filter. But the point is multiple sizes of filter are applied in parallel, and then their information is concatenated, is regrouped into this final layer before going into the next layer in the convolutional network. So it's quite complex. But I think an intuitive way of looking at this, at least the one that makes the most sense for me, is what convolutional networks do is they look at a bunch of pixels, and then they say, okay, if I take those 16 pixels, what do they mean? And that's the way we look at image too. We don't look at pixel black, pixel red, pixel yellow. We look at the image from a distance, and it's the association of the different pixels together that give us edge, that give us images, that give us meaning. So in a way, a CNN does the same thing. But I said that the problem is that convolutional neural networks are actually really hard to train because they require a lot of data, okay? Because there's such deep neural network. So what we've done is we've applied a relatively new idea in the domain of machine learning, which is transfer learning. So what is transfer learning? So imagine that you have a network that is trained on a very large data set and gives you a really nice model with a lot of labels. And now imagine that you have another data set that is kind of similar in structure to the big, large data set, but is much, much smaller. What you want to do in transfer learning is you want to assume that the bulk of what this model has learned from the large data set is applicable to the small model. So you basically move the learning, you move the model from the pre-trained model from the large data set to the small data set, and you only retrain the classifiers, so the last layers of this particular architecture. And again, the idea here is that the structure of the data that you look at is very similar, so that learning in one domain is applicable in the other domain. So that's kind of interesting in geosciences, because we really are actually not a science that has large data in the sense that big data understands it. But it raises a question, and the question is, you know, if you have a network that is trained on this bunch of data, okay, so images of cats, dogs, cars, whatever you want, and if what you're really interested is to classify this, you know, at first, as a human, you look at it and you say, completely different beast. But you have to think the way a neural network works. And actually, for the neural network, these two data are very similar. They're both images. They both have pixel of a certain dimension. Those pixels have an RGB component. All of these, basically, the way you recognize feature is through saliency. It's through looking at edges and contrast. So there's a lot of commonality between our rocks and a runner or a dog. And that's the sort of stuff that we can actually hopefully transfer to a network. And we tested that. Sharinya was my master's student in 2018, and her project was essentially a pilot study to test this idea of transfer learning on Inception, which was trained on those cats and whatnot, to a geological problem. So what she did is she took Inception, and Inception is trained on 14 million labeled images in about 20,000 categories. There is no way any of us will ever get to that size of a data set. Okay, so that's enormous. So all we had to do then was to basically train the final output, train the classifier, and Sharinya did that in 7 categories from the Dunham classification using just 35,000 labeled images. That sounds like a lot, but for neural network, it's not a lot. So let's see what she found. So first, the data set. Where was the data coming from for Sharinya's project? Well, we worked on cores from the Marian Plateau, not because it's the greatest place in the world, but really because I had scanned those cores myself, and I had tons of data that we could use. So it was a target of opportunity, good carbonates, nice, clean, and scan at high resolution. And what Sharinya did is a fairly standard data science approach, where she took the scan section, that's 1.5 meter of section, and she looked at a small image from those cores. So she was able to extract small images of 4.5 by 4.5 centimeters, okay? So you can see from one core section, you can get multiple images. Then this image was labeled, okay? So that means we gave it a textural name, such as Mudstone. And then essentially we train our network the way I've showed you with a simple neural network, you would do it. So you basically feed forward that data with the label. The network knows whether it has the right or the wrong answer. And if we're happy with the accuracy, then we stop training. If we're not happy with the accuracy, what we do is we change what are known as the hyperparameters and retrain. Hyperparameters are things that the network does not learn from the data, but that you have to input yourself, such as the number of epochs, the size of the batch, etc. I won't bore you with the details. And we stopped once we had a high enough accuracy. Notice that we also tried to use random forest, but the results we got with random forest were relatively limited in terms of the accuracy. Right, so let's jump straight into the results. So here's a fake core where Sharinya put together 3 different lithologies. And what you can do now with the trained network is you can feed him, or it, I should say, this core. It will basically slice it into small squares. And each one of these small squares is going to be independently assessed for a texture. And you get something like this, where you basically have a textural classification at the same resolution as the input squares, okay? If you prefer to have a more traditional curve, you can also just look at the average classification per row and output something like this, where you basically go from Rudstone to waxstone back to floatstone, all right? What I think is really interesting and something that is important to realize is that these are statistical models. So at the end of the day, what they do when they do a classification is they come up with a probability of the sample belonging to a certain class. And you can look at this probability, which means that if you look at some of this classification, you know, when you're in the 40% sure that it's a packstone, you might want to revisit this one. Okay, so it gives you an output as an output a QAQC value immediately. So that is, you know, to use this type of technology is 60 times faster than if a human was doing it on their own. So it's very, very fast. Once you've trained your network, it's super fast to do the cores. The resolution is also 10 times higher than you would normally describe a core, you know, which might be a good thing or a bad thing if you don't want too much data. But anyway, it is at a much higher resolution. And the accuracy is actually not bad. On this pilot study, we obtained our best model was 88% accurate, meaning that in 88% of the cases, we got the right answer. So let's look at where the errors were, because that's interesting. So what I'm showing you here is a confusion matrix. It's not the last one you'll see in this talk. So it's important to spend a bit of time to understand what a confusion matrix is. A confusion matrix shows the class of your data, the test data that is also labeled. I forgot to say that we keep 20% of our data set to test the final result. So that's not trained, the model is not trained with that data set. But we know what the classification of this data set is. So that's a true label versus what the model predicted, okay? If you are on this 1-1 line, so the diagonal of the matrix, it means you have a true positive. The model predicted accurately the classification. So we can immediately see where the main source of error is. It's in floatstone that are misclassified as Rudstone, so finer lithology misclassified as coarser lithology, whereas the Rudstone misclassified as floatstone is more rare. I'm also showing this here, maybe it's a little easier to see. The floatstone Rudstone, you can see that basically it tends to see, the network tends to see more grain in the texture than there is really in this texture. And the same applies actually to the wax and packstone texture, although it's more subtle and less easy to see. But the good thing is, despite that bias, that model is very reproducible. So it will tend to have the same bias over and over again. So the question then is, are humans any better than the network? Okay, so I showed you the confusion matrix for the network. What we did, which was a bit sadistic, we took those difficult to classify Rudstone, floatstone, and we gave them to my PhD student and former postdoc and colleagues. And we asked them to classify them without telling them what they were. And that's the human confusion matrix. So again, that's so these are number of instances. So that's the floatstone and the rudstone. The true actual classification is here, and the predicted classification is here. So are human better? If you look at the previous matrix, the neural net has an error on these two lithology of about 23%. So 23% of the time, it will misclassify a floatstone for a rudstone or vice versa. Humans, 45%. So much higher actually than the network. Now, don't get me wrong. We did not do an exhaustive study. We did not, have hundreds of people looking at this. Not everybody was like an expert with 20 years of industry experience, of academic experience. So I'm not suggesting that these numbers are very representative, but still they're very intriguing and interesting. And I think they show you where, this technology can be extremely useful. Now that bias of seeing grains on a boring or relatively monotonous background is actually a human bias known as saliency. And it evolved probably because seeing something that moves or that a shape that comes out of a background like a savanna grass is good for survival. So we know that humans have that tendency, but why does our neural network also show that tendency? We'll see later that we have an idea of why this might be the case. But before that, it's one thing to train a neural network on carbonates from the Marian Plateau, which is, Miocene carbonates. If you know anything about carbonates, they evolve through time. They have different critters, they have different organisms, they have, different texture. Yet you can still apply, of course, the Dunham classification. That's not a problem. But the question is, did our network learn truly to classify carbonates, or did it learn to classify carbonates from the Marian Plateau? So to kind of check this, we did a quick test on other cores. So we trained everything on the Marian Plateau, but we used the Maldives dataset to test our network. And as you can see on the Marian Plateau, we have rhodolites, we have benthic forms, coral algae. On the Maldives, we have a rich diversity of fossils, encrusting algae, branching coral, gastropod, bivalve. It's very different. And yet, and here I'm just showing you the floatstone and the rudstone that we tested extensively. And yet, if you look at the accuracy on the Maldives dataset and the accuracy on the Marian Plateau dataset, they're the same. So it does seem that what we've learned on one dataset is applicable to the other dataset. So that's kind of encouraging, and it certainly encouraged us to be a little more cocky. So we decided, okay, so we train an algorithm on cores. What if we apply it to thin section? It's never seen a thin section, but an image is an image is an image. Okay, the scale is different, but let's have a look. And we gave it essentially one of the thin section of the Lockyer and Janabi paper. That's a floatstone, okay? And long story short, in blue, you have the results published in the paper. That's the human classification. Only 40% of the participants thought it was a floatstone, but everybody said, yeah, it's very easy, okay? And then you have waxstone, mudstone, packstone, etc. What the network does is it outputs a probability of this being a floatstone that exceeds 98%. Okay, so it's pretty confident it's a floatstone, and at least in this case, it's correct. So again, the network surprisingly does very well on this type of material. So all of that, all that I've shown so far is basically part of a paper that's in prep and should be submitted very soon. But we have current work. So now I'm going to change track a little bit and talk a little bit about the current project within my group. And I'll start with the PhD project of Harriet. And Harriet, in a way, took these initial results and are pushing them to the next level. So she started less than a year ago. So we have just a few data to show you today. But already you can see that Harriet has a total data set that is larger than what we had with Sharinia. And the goal is also to have a more diverse data set. So if you have data that you want to share with us, you know where to find me. We'll welcome your data. We need it. But we mostly focus on IODP data because it's publicly available. So what Harriet did as well is she tried to train network with different architecture. I've shown you Inception because that's what we did with Sharinia. We also knew that Inception had a very high success rate with other data sets, so why not with ours? But what about other architecture of CNN? Because there are plenty of architectures out there. So what Harriet has done in her first 9 months of PhD is to try 3 architectures. So Inception V3, she's retrained it with her data set, VGG19, and ResNet 50. And you can see the accuracy is still a bit low. Don't worry about this. This is still work in progress. We still have a few wheels to tweak. But that's not the most interesting part of this initial result. Actually, this initial result is very exciting. Because if you look at the confusion matrix, again, remember true label versus predicted label here, that confusion matrix, whether you look at VGG19 or ResNet 50, is very similar. You can see it's the same floatstone, Rudstone confusion, floatstone, Rudstone confusion, and essentially the errors are distributed almost exactly at the same location, all right? So that suggests that it's not necessarily the architecture of the CNN itself that's the problem that we have currently, but the potential source of errors could be the fact that we have, even though we use transfer learning, we still have too small of a data set. So that's a potential issue. We probably have an uneven class distribution. And as a matter of fact, we know we have an uneven class distribution. By this, I mean we have more of the Mudstone than the Rudstone, for instance. And that is a problem when you train your network. You want to have an even distribution of classes. So again, A and B mean we need to get more data. Well, that's not too hard to do. It's time consuming, but we can do it. But there's also the potential that there is a bias in the interpretation of the individual PhD student or master student who does that work, and that's a serious problem. I don't think that this is what's biasing those 2 architecture, because the error is so similar. But nevertheless, you don't want to spend all those years training a network that essentially has the same bias as one individual. You want to have something that is a little bit more reliable. So Harriet is doing something that I think is really interesting. She's working towards a project that falls under the category of citizen science. And the idea of citizen science is to basically gather people that are either expert or non-expert and ask them to contribute towards data science. And in our case, that would be to overcome the classification bias. So we're working on a project in Zooniverse, which is one of these citizen science platform that you can use. And this is essentially their advertising straight from their website. And Harriet is currently putting together a project that needs to be peer-reviewed and approved by the Zooniverse project, where all of our data will be online, and people will be invited to come and classify those thin section and those core photographs. Now you might think, hang on, you need to be an expert for classification. Well, it turns out it's not true. You can actually do complex classification without really understanding the science, as long as you're given some graphical example of what to expect for each class. And that has been done for biology extensively, for medical sciences, for astrophysics, but geosciences, we're a bit behind. Okay, so the idea is we want to have this Zooniverse project finished by the end of the year, so by the end 2020, and then we'll need your help for the classification, because the way these citizen science project work is we get multiple people to classify the same thin section or image, and then you look at statistically where the average is, and generally that's the true label. And that's a way of overcoming the bias of one classifier. But we don't only work on core images. I also want to briefly mention another project that is kind of a departure from what I've presented so far, but is along the, in the same vein. It's the project from Sarah Baharuddin, and she put together that very nice slide for me to present. You see the very friendly robot here. The idea here is that we want to use another class of neural network known as GANs, or generative adversarial networks. And these are the sort of networks that are used if you've seen these applications that can transform a photo into a Van Gogh. That's the kind of technology that we're using here. And the idea is to take a formation macro scanner, so essentially where you look at the resistivity image from a downhole log, and transform that FMS, or formation macro scanner, into an image of a pseudo-core, because that is easier for a geologist to describe than that, or for a network to describe than that. So I'll show you some initial results here. So Sarah has used two different types of algorithm. One is supervised, one is unsupervised. And these are very early results, so they just give you, it's really like a teaser. It's not the final results, but you can see here's the source FMS image. Here's the label, which is the real core target image. Okay, we focused on relatively continuous, boring, bioturbated carbonates for the moment. A target is to make this actually more diverse in the coming weeks. And Cyrus results here show that if you use the supervised approach, at 10 epochs, remember an epoch is when you see all the data set at once. It's still a small data set at the moment. Well, kind of looks like it, but not really. But once you go towards 50 epochs, which takes a long time to train, you're starting to see structure that are looking more and more similar to the image that you started training from. It's still not perfect. We probably need to go to 100 epochs or more. We need definitely more data. But this looks like a very promising start where we should be able to translate from the FMS image into the core image domain, which I think is exciting, cool, and hopefully useful as well. The other GAN that we use is unsupervised, and I think we're probably not going to go very far with this because you can see that the image here of the core looks much more like the FMS than it does look as a core. So most likely we'll have some limitation with this particular type of algorithm. But that's kind of the backbone of what you do with this data science machine learning project is you test multiple architecture and you try to improve your results. Now, university is not all about research. It's also about teaching. And data science, including machine learning, is really a skill that is in growing demand. And I think in earth science, we're somewhat behind the curve. If you look at biology or medicine or other sciences, they were on the wagon of machine learning before us, but we are catching up. So there is a demand both in industry and in academia for this type of technology. But it's sometimes hard to bridge the gap between hardcore coding and geology. I coded as a kid. I loved it. I almost went into computer science. So for me, that's kind of, I'm merging two passions here. But for someone who comes with an earth science degree, sometimes it's a bit intimidating to go into this type of project. So I'm very happy to announce that I proposed a course to the department, which has been accepted. It's a new course. It's an introduction to data science. I like to call this Earth Data Scientist or Earth Data Science because this course is going to look at the specific of Earth data. It really will be introductory level, okay, where I'm not going to form fully fledged data scientists in 5 days. There's just no way that's going to work. But at least it will give a taster to our student of what data science is and how to use the different tools and understand the lingo, which hopefully when they join a company will make them much more able to talk to data scientists or data engineer within their company. And I welcome any data you might have or data set that you would be willing to share for me to use in this course. Any feedback or discussion on the course is very welcome too. Well, that leads me to my conclusions. I'll leave you with some very simple conclusion. I think that machine learning, especially deep learning, really has a lot of potential in terms of a revolution for geosciences. And I think in the coming few years, you will see more and more of these applications. They're already here, and it's just going to be the norm. And I think looking at what we're currently focusing in the group, the application of deep learning to geological images, whether they're core, thin section, outcrop photograph, micro CT scans, etc., is extremely promising. And I think the technology is here. You need the know-how, but we should be able to extract a lot of really valuable information from this type of data. But it's not limited to this. This approach can also easily be translated and extended to other types of data. For instance, seismic images, which is also something that I'm quite keen to explore in the future. And finally, this is a kind of a plea, for research, resources are needed. So we always welcome and we're always looking for industry partner. Obviously, sponsorship and money for research is, like the gold standard. However, I know this is not the right time with the current economy to really ask for money. But even data or projects and collaboration with the industry partner is something that is really valuable to me and to my research group. And it's not just industry, it's also academia or any collaborators. If you have data, if you want to volunteer for classification, exercise like this Zooniverse that we're putting together, then please contact me and we'll find something for you to do. And with this, I'll leave you with a little bit of a joke, and I'll take any questions that you might have.
Thank you very much, Cédric.
You're welcome, Catherine.
Really interesting talk, and a very complex subject that you've managed to make very, very straightforward in a way.
Good, I like to hear that.
Fantastic. So we've opened the chat for questions, so please ask away, and I'll read out questions for Cédric. If you're watching this as a recording, there will be a thread on the forums. At present, our forums are down for maintenance, but when they're back up and running, then please go and ask your questions about this topic on those threads. So our first question then for you, Cédric, is from Dai from South Korea, who asks, can this method be applied to siliciclastic rock? Have you ever tried on this type of sedimentary rock?
Yeah, of course it can be applied to siliciclastic rock. There's absolutely no reason why it would not be applicable to this. It has been applied as well, to my knowledge, to plutonic rock and basaltic rocks. You know, it is something you can apply to any type of data set, really image data set. The reason that, no, I've not done the classic, and the reason I've not done the classic is the carbonate is a little more tricky. So it makes it a more interesting and challenging target. And it turns out to be my specialty, but you know, I'm not averse to try it on classic if we find the right data sets. But for now, we're focusing on the carbonate just because of the challenge. But yeah, that's a good question.
Great. Next question's from Jaco Bass. Thank you for explaining a complicated subject so lucidly. I see lots of potential beyond carbonates. I was wondering, in the confusion matrix, how do you know that the true rock type is correctly classified? What is the human error in true? In other words, could the neural network make a better prediction than the person who defined the true rock type?
So no, the neural network cannot make a better classification than the human that described the rock, for the simple reason that what the neural network knows is the label, which was classified by the human. So that's what I was trying to explain with that Zooniverse project. The problem is, as long as we have one individual classifying the rock, you know, if that one individual has a slight bias, and I think all of us have potential biases in terms of our core descriptions, then that bias will be translated to the train algorithm. So the network doesn't have an independent way of judging the quality of the data. It basically just takes the label. If the label is wrong, that is going to make that is going to have an impact on the accuracy of your final model, your final predictive model, essentially. So that's why it's important to move away from this, you know, small data set, one person describes it, and go to something where we have a statistical description of the data and we're kind of confident that the label is correct.
Cool. Our next question is from Noel Silby, saying, thank you for sharing this great work and discussion. I'm interested in numerical geology, and I'd like to ask about accuracy and error and how that can be calculated.
Yeah, so there are multiple ways to calculate accuracy and error. And there are multiple metrics you can use. You know, one of them is to look essentially at the ratio of the true positive, so the true classification, over the true positive plus false negatives, and look at that ratio. And so there's plenty of ways you can try to classify how your model is doing. So either you're going to look at precision or you're going to look at accuracy, but you have to choose which one you want. So in other words, you have to know what you want. Do you want a model that will be able to not make a false negative because it's important to you? So a good example, when you read about these examples, a good one is in the medical domain, for instance. You know, if you're trying to find a tumor, you can live with a model that gives you false positive because it's a fright, but you know, you can quickly do a second test and realize, no, that person doesn't have a tumor. It's much more problematic if you have a false negative. In other words, when the person has a tumor, but you don't detect it. So you are going to use a metric that favors essentially the detection of those tumors, even if you over detect them. So these notion of, I mean, it's a bit of a complex answer to a simple question, but the thing is, it's a very good question because what you are going to use depend ultimately on what you want your model to be able to do. And how you're going to train your model also depends on what you want your model to be able to do. So you have to choose which metric to use, whether you want a high precision model or a model with a high accuracy, and these two are not compatible. It's one or the other.
Cool, great. Stephen shared the paper that you mentioned in your talk on the Dunham classification.
A great read. It
yeah,
scared me for weeks. And then inspired me to do that work.
So yeah, anyone else who would love to read that and be inspired, just download that from the chat. Next question is from Jonathan Osmond, who asks, is from the University of Oslo, and asks, I'm not too familiar with what is available now, but my impression is that one must search for tools that you need to perform identification with machine learning, and a few standard software packages that offer those types of tools. For those who don't have large data sets but would benefit immensely from these tools, are there easy tools that are ready now? And how do you see this becoming more widely available to the majority of geoscientists?
Yeah, so I think you have to distinguish between, you know, applying a model and training a model. So the application of a model, the way this this technology works is the training is the hard bit. Once you have a trained model, it takes not a fraction of a second to classify a rock or, you know, whatever you give it to classify. And it's very easy then to deploy this into a nice graphical user interface, etc. Now, there are packages that are essentially that don't require you to do any coding, where you can actually do train your own algorithm by using different approaches. There's the Weka, for instance, is a very well known. It's actually a library written in Java. It's a machine learning library, so you can use it as a programmatic library or an API. But they also have a nice graphical user interface that allows you to basically import images, train a network, and do things with it. But the truth is, what you can do with it is relatively limited if you want to push the envelope of the current technology, because, you know, to be able to get better results, you need to do new things. You need to be able to use the latest technology. You need to be able to, something I haven't talked really is how you prepare your data, which is immensely important for how well your network is going to be trained. And all of this, really the power of coding is that you can do it all, you know, and it's actually not that complicated today. You know, you have some tools that are available, the Jupyter Notebook, if you're familiar with it, which allow you to do small snippets of code, you know, and you can use Python. Personally, I'm not a fan of Python, but anyway, here, you know, it is the most used language for that type of approach, and it has amazing libraries. So it has tools that are very, very well designed for this type of data science approach. And you know, it really gives you the power to do this work. But for those of us who don't want to code, what's the future? Well, the future is using tools like Schlumberger is producing, or other major companies are producing, which essentially have an already prepared algorithm that has been pre-trained. The problem, of course, well, I'm in research, so you know that's kind of less satisfying for me. But beyond that, the thing is, you depend on the black box, and you don't really know how the algorithm was trained. And again, if you want to do something that is slightly different to what the tool is capable of doing, then you're back to square one.
Okay. Next question's from Pedro Fernandez, saying, thank you very much for the clear explanation. Have you had the chance of applying NN to a complete core? If yes, how is it matching with the classical geological description?
We've not done that yet, actually. It's a good idea. So the closest thing we've done was to apply it to that pseudo-core to show, you know, if we put very different lithologies next to each other, will the algorithm actually catch this? But we've not really gone into, you know, the exercise of trying to describe a whole core. The reason for that is we feel, I hope I showed that with the current project from Harriet. We feel that we can push these. Right now we have about 10% error, 10 to 15% error. We feel we can push this to get a 95% accuracy or something like this. And we really think, which is a classical machine learning problem, that the main issue is the size of the data set. If we get a larger data set with more labeled data, we'll get a better algorithm. And then comes the time to do actually something like a case study where you apply it to a kilometer of core. Because I think, I forgot the name of the person who asked the question, but yeah. I think this person is right that this is ultimately what these networks will be useful for. And I think for me, the good thing is that means you can describe cores in basins that are thousands of kilometers apart with the exact same criteria, which is always a problem. I always tell my student this story. When I was describing cores from Leg 194, I was a PhD student myself on the joyless resolution, so for ODP. We had a night shift and a day shift, and we got very excited because we had cyclicity, and we thought, that's maybe marine cyclicity. Well, I'm sure you'll guess it. What it was the night shift description versus the day shift description versus the night shift description. And luckily, we picked it up before the end of the cruise. So we took all the core out, and we spent 2 hours overlapping the two shifts, and we came up with a reconciliation of how we describe cores. But that was kind of like an early sign for me that different teams will describe cores differently, and when you put these descriptions together, they look different.
Very interesting.
Yeah.
Our next question is from William Harrison, saying, hello, I'm a PhD student in the Netherlands and was wondering if you have trained your AI to identify carbonate rocks in thin sections as well as cores.
No, but that's the next step. That would be the next chapter of Harriet's thesis. She is in the PhD for less than a year, so we need a bit of time. And also the data set. Again, cores are relatively easy to gather. Thin section images, getting 30, 40,000 images of thin section is a little trickier. At least I don't have my hands on them right now. So that's a plea. Send me your thin section images.
Great. Next question then is from Diana Ortega Arisa, saying, great talk from the Kansas Geological Survey. 2 questions. 1, what software do you use for this type of analysis? And 2, have you applied the method to outcrop images?
What was the second part of the question?
Sorry, have you applied the method to outcrop images?
Oh, right. Okay, so I'll answer B. No, we've not applied the methods to outcrop images, but there is no reason why we could not, as long as we have a high resolution image of the core, of the outcrop. And of course, then you have the issue of weathering, which is a problem even when you describe the rock, yourself at the cliff face. But yes, absolutely, that's a logical thing, should be doable. So the software that we use essentially is a combination of Python coding. We use a library known as TensorFlow, which is a widely used library for essentially neural network training. And we usually do this in a Jupyter notebook, which is like the standard tool set that a data scientist would use. But you can use whatever tool you want, whatever IDE or programming interface you want. But yeah, it comes down to essentially writing code for this. Now, to prepare the data, I know that the students use various approaches. Sometimes they can use Illustrator or Photoshop to parse the data into smaller images. So there's also some manual work that takes part before the coding that is part of our workflow.
Cool. Next question's from Gillian Ivy. She says, hi, I'm Gillian from Queen's University, Canada. I'm interested in your intro course for coding for geoscientists. Do you have advice on where to begin when trying to integrate coding to geoscience research and which coding languages to start working with?
Yeah, no, that's a great question. It's something that I've been also thinking a lot about myself, because I think I've kind of like revealed that in terms of the language itself, I'm not a fan of Python. I find it harder to read, and there's a lot of, I don't want to go into the technical details, but there are things that I'm not particularly fond of in Python. So my favorite language is Scala. However, when you want to do data science, the path of least resistance is to use Python. So I would recommend use Python, because the libraries that are written in Python, first of all, they're all there, they're all new. All the new ones are written in Python first, so it makes sense. And Python is a relatively easy language, which means it's easy to learn, but that's also part of the price you pay afterwards, because it's easy to learn. It means that it maybe lacks a little bit of the sophistication that other languages could have, but that's really kind of a detail. So how do you learn to do this on your own? There's really a lot of training videos out there. There's a lot of really good books. I don't want to do a recommendation online now, but I can, in private, I can make a recommendation of those that I enjoyed reading, for instance. So I learned by my own, for instance, and then I don't know if that person is a teacher or a student, but if you want to design a course, I think the thing would be to basically kind of like look if there are any data science courses around you that you could join, or learn on your own, and then integrate. I would say keep it simple. If you're going to teach geologists to do data science, don't go too far. Keep it simple. I think it's better to understand the basis and give them the tools to be able to learn further later if they decide to go that way, but also a good overview of what the field is, what the typical pitfalls are, what the typical benefits are, what the different classes of algorithms are. And at least I intend to do this as a practical course. So rather than do a lot of theory and a lot of math, just sit in front of a notebook and code. And even if it's rough at first, in 5 days, hopefully they'll be able to understand what they're doing and have a practical, pragmatic approach to the topic.
Great. Next question is from John Reimer, saying thanks, very interesting talk from Doran KSA. Will it also work on outcrop panoramas? I think we've touched on that.
Yeah, we've touched on that. It would need to be tested. Again, I think the main problem with outcrops would be the weathering, which might make it, which might throw the network off. But it would not be hard to add outcrop data to the training set as as just like another dimension and quality of image. But you want to start simple, and then you want to build on that simple. If you start complex, it may not work.
Speaking of which, next question is from Dai from Korea. Again, they want to know about combine two variable models such as seismic and core data to predict in larger scale. So is that something in the future?
Yeah, that is something I've been talking to people in industry about, where you'd want to do, because it's a natural thing to do, right? To take multiple data set, and you always have in geological data set that representative volume, and that gap of the scale of observation is a big problem. And I do think that these technology have a role to play there, where you can nest observation at different scale or from different data sets into one model. But you're talking about a large scale research project here. You're not talking about something we'll do in 6 months. But that definitely is something, given the proper funding, is something that we have a very keen interest on doing. And it's obviously a good idea.
I think William Housen is going to be in touch with you about collaborating with Insections.
Fantastic. I'm looking forward to that.
Next question is from Mel M, saying, from Scotland, saying, prompted by the comment about cyclicity, your training is based off individual images. Will it remain that way, or will you also be retraining it off from classified whole cores when you get to that stage? I'm wondering about the spatial component, as the presence of neighboring mythologies may perhaps bias the human labeling.
Yeah, this is a good point for the human element. And the answer is no, I don't intend to retrain on the whole core. Because if you think about it, so the Dunham classification was developed on thin section. So it's a description in the small, I would say. So having those relatively small vignettes and outputting multiple smaller classification on the core, in my opinion, is the way to go. And there is the network is not biased about what happens previously. It has no sense of the timeline that the core represents. It just gets a piece of data and then it outputs a classification. I think this is what it should do for this particular approach. However, there's another aspect to it, which is, if you wanted to apply neural network to something like understanding cyclicity or understanding base level change, sequence stratigraphy, which is something I've had a thought about, you'd want to use a neural network that has a time component, where essentially the previous results impact the current classification. It's not necessarily valid for a descriptive network like the ones we're working on, because a Rudstone is a Rudstone, no matter whether before you had a Mudstone or before you had a Packstone. However, a particular lithology might represent a low stand or a high stand above, a certain sequence boundary based on what the previous lithology was. So if we were to go into that direction of trying to interpret stratigraphy, then we'd want to use other types of architecture. And recurrent neural networks are the ones that seem to be the most appropriate for that type of application, not the CNNs we're using.
Amazing. Thank you so much to everyone for your fantastic questions, and thank you very much to Cédric for answering them so well.
Thanks for having me.
So just if we'll say thank you again to Cédric for coming along and giving us an excellent talk and introduction to machine learning and carbonates. And hopefully we'll see you next week at our webinar from Peter Burgess at the University of Liverpool, who's going to be talking to us about, his talk is called A Big Fan of Signals, ? Exploring autogenic and allogenic processes in low byte 3D, a numerical stratigraphic forward model of submarine fan development. So that sounds really fantastic, and I look forward to that too. If you'd like to suggest a future speaker, all the forms are available on sedsonline.com. And if you haven't come to a coffee break yet, come along, say hi. There'll be one in your time zone. And actually at this talk, we've had questions from South Korea to Canada. So that's zones 1 all the way to zone 3 on our coffee break. So please come along, say hi, and we'd love to meet you. So without further ado, I think we'll see you all next week. Thank you for coming. Thank you, Cédric.
Thank you very much, Catherine and Stephen.
Bye.
Bye.